All right. This is going to be the beginning of our module on databases, specifically on what are called relational databases, which we've seen a little bit with Postgres, but we're going to dive deeper into. So these things are a huge deal in programming. Managing data, storing data, retrieving data, organizing my data. And with Postgres and SQL, we'll learn about tables, columns, relationships between tables, and we'll at least open the door on some more advanced things like indexing and optimizing queries. So we're going to learn how to build and maintain efficient and scalable database systems, right? And this is super important. And I've kind of thrown a couple of quotes here to talk about the importance of data, because as we write programs, we focus so much on logic that it's easy to lose sight that the data is actually way more important. One of these quotes is by Linus Torvalds, known for creating the Linux OS, the open source version of Unix, and the version control system Git that we know and love. And this quote is, bad programmers worry about the code, good programmers worry about data structures and their relationships. And that might be a little bit overkill, but it does capture an essential truth. This other quote is by this guy, Fred Brooks, who wrote this book called The Mythical Man Month, that's consistently considered kind of like the number one software engineering book of all time. Um, Back in the 60s, he was the lead architect for IBM for one of their giant mainframes, back when big mainframe computers that might like take up like a whole room were how computers worked. So if I was a big bank, we had like one mainframe running in the basement that like everything for the company ran on. And this quote is, "Show me your flowcharts and conceal your tables, and I shall continue to be mystified. Show me your tables, and I won't usually need your flowcharts. They'll be obvious." Right? And just to show how old this quote is, this is back when programmers designed programs, they made flowcharts first because of how much of a time-intensive, laborious task actually programming was, right? This might even be back in the days with punch cards. So today, we're really getting introduced to the structured query language, SQL, and to databases and relational databases. So part one of this lecture is more conceptual. We're going to talk about what is a database, what's a relational database, why do they matter, some of the ideas behind data modeling, and we'll talk a little bit about best practices and some Postgres fields. And I'll give a preview of relationships. Part two, we'll get more hands-on. We'll deal with the Postgres database engine and the pSQL command line client to talk to Postgres. We'll see how to take a schema design or a database design and turn it into tables. We'll see how to run SQL files in Postgres, import CSV data, and update and alter various fields, and in particular, a primary key for when we're importing data that has primary keys. Some of this we've covered before, so some of it will be review, but some of it will be new. Do folks have any questions about what we're covering here before we dive on in? Tom, yes, sir.
How much of this from the previous weeks are going to have to remember to be able to make sense of what we're about to dive into?
We're gonna cover it all from the ground up.
Oh, okay.
Yeah, yeah, for sure. Yeah, it's a good question. Um, let's, but part one is going to be more conceptual. Um, I'm not going to go through this whole schema design doc yet. I'm going to talk a little bit first about basically what are databases and relational databases, why do they matter. I am just going to talk through this bit. When we talk about schema design or database design, we're talking about defining the structure that's going to represent how we organize our data in a database. And as our programs get bigger, having a well-organized database schema is really, really important to ensure our data stays organized and is always correct. Data integrity, performance, maintaining the code and ease of use. So before we dive into this, let's just review a bit about where the database fits in. So for the last several weeks, or the last week or so, really, we've been focusing on what's called the front end, right? And so we might have the user and they're using their browser on their computer and they're talking to over the internet a server, right? And maybe this is my app uh, server, and this is going to host the front end React app and host our REST API. And so, maybe in fact we're building a Pokemon site that we know and love. And so the user talks to my server and they're requesting my web page and my server sends it on back. And at this point, we now have, say, our React app running in the user's browser. And now my React app might start asking things of the server, right? It might ask it for information on a specific Pokemon. And the REST API server is going to send back some data. And obviously there would be more data than this, but just in the interest of time, I'm going to keep this simple. And then here in the app, we would do stuff with this. And this is, again, to kind of pull up the Poke API as a reference. But this is what the Poke API REST API does. Right? My React app is going to send this GET request, and rather than the browser like displaying all of this, my JavaScript running in the browser, my React app running in the browser handles this and makes a really nice user interface to catch all the different Pokemon. So there's all this data to be stored and organized, and the data might change. And this is where the database comes in. And I'm going to use an oval. You usually see databases drawn as a cylinder, but they don't have a cylinder here. And let's make our database green. Why not? And let's say that we are using Postgres. And we are going to store all the information about an individual Pokemon here in our database. And so for a relational database, we create what's called a table. And it is going to have different columns, kind of like a CSV file, right? And it might, have whatever. And there might be other data that I want as well. Pokemon have, for instance, Pokemon have different moves. And let's just say our Pokemon has one move. And we'll just give it like an ID. And so our React app then might say, hey, you know what? I actually want to get like information about that particular move. and I don't know enough about Pokemon. Does anyone know a good like Pokemon move name? We'll just say like awesome move, right? And so now our database has two different tables storing these moves. Um, and when I'm talking about a relational database table, I think the right metaphor really is a spreadsheet because in fact, most databases consists of rows and columns. So we might see, say, for our Pokemon, a row, right? So we have row columns in our table, and each column has a name. And I realize that I'm kind of building this up, but we're going to build this up step by step. And then there are rows of data. And in fact, back in the day, you could imagine like an actual book, like a ledger book or something that had these things. And so I could have what's called a table of Pokemon, and then I might have a table of moves. And I could have all sorts of, again, I have rows of data here, right? And columns. Um, and we've seen with CSV with comma separated value data, I can store this data, right? If I want to, I could do, um, Pokemon.csv and it would look like this. And I'd have a moves.csv file and it would look like this. But we start to run into limitations, right? I want to make sure that I want to be able to have rules. I want to be able to make sure that like every Pokemon's move exists in the DB. Like I don't want a Pokemon to have a move that doesn't actually exist. I want to make sure that, every Pokemon has a name, that the name is a string, that it's not more than 20 characters long. I might have other rules I want to put in there. And then I want to make sure, every move has a name and that the name is a string and the name is not more than 50 characters long. Maybe there's some super long move names. Um, and as I start to add more data, more columns and rows, I would have more rules, right? And then I might even want rules about relationships, right? What if I want a Pokemon to have more than one move, right? What do I do here? Would I want to start modifying my data so that I have to go like this? Would I want to start modifying my data so it's sort of some weird, like nested kind of thing? And then what if I want to do things like see all the Pokemon that have, the awesome move. And in fact, as my data gets more complex, I might even need a separate table just to keep track of Pokemons and moves. And we might, and it might look something like this. And now, if I want a Pokemon to have multiple moves, now Pikachu, the Pokemon with ID 1, has both the awesome move and the decent move. And this is getting more advanced. We'll talk about this in later lessons. This is called a join table. But I wanted to lay this out to illustrate some of the real world things we might want to do and some of the challenges with working with our data as it gets more complex, right? And as we've seen with the Pokemon API, there is an awful lot of data. And it might be constantly changing. If the Pokemon game was brand new, maybe Nintendo's pushing out new Pokemon every week, right? To like kind of keep people excited and stuff, or there's add-ons or things. So there's a lot of data and it could be constantly changing. So this is actually a great example of what we talk about when we talk about relationships. And again, imagine doing all of this on paper. I might have pages and pages of Pokemons in graph written down on graph paper, pages and pages of moves, and then a big old list of which Pokemon have what move. Right. And in essence, this is what a relational database does. It structures our data. Right? It structures our data. It enforces rules about our data. So our data is always organized and of the correct type. And it tracks or models relationships. And that's what we're seeing here with this idea of IDs. And then it makes it easier to query, to learn about our data and get specific data. It makes it easier to modify our data. It makes it easier to modify the data schema. And it also protects what's called data integrity. For example, if I'm writing code for a bank, what if a server crashed right when we were inputting new data? What if I was withdrawing money from my checking account to send it to your checking account, and I'm right in the middle of that transaction and somehow the server crashes? Um, I don't want to have money like pulled out, but not recognize that it was put in, or even worse, like money from the bank's perspective, like money put in that wasn't pulled out. So there's this idea of a database transaction and database engines, like they'll make sure that something gets like saved to the file system and saved in multiple places before telling us that it's complete. And there's this idea of what's called different layers of a data model. And we're not going to get too much into this, but at the highest level is what's called the conceptual model. And if we're Nintendo, we might say, hey, I want to be able to talk about Pokemon and they have different moves. And, the Pokemon should have a name and the moves should have names. And that's sort of at this conceptual level. Then as programmers, we might say, okay, cool. I should probably make a table for Pokemon, a table for moves. I should think about those relationships and stuff. And I'm going to write SQL to do that. Um, but then I want to make sure that like when this data is changed, it's saved on the file system, it's saved correctly, that if a server or a computer crashes or the power goes out, that everything isn't lost. And this is what we call the physical model, right? And the nice thing about this is that really I don't have to worry about this too much. This is really what the database engine does for me with modern technologies, is a lot of things around data integrity and backups and so on. And in fact, to go back to our diagram here, what ends up happening if, say, we really were Nintendo, it's not enough to have my data on one database. I might want to have multiple database servers that my program can talk to, both in case one server goes down, there's a backup, but also we might be getting so much traffic that we need to have multiple versions of the database, and then they kind of talk to each other to keep stuff in sync. And this is called a database cluster. So this is getting more advanced. But the point being that as like our applications start to get fancier, the architecture starts to become more important and keeping track of our data becomes more and more important. So I've been doing a lot of talking here. So I just want to pause and check in and see like what questions people have, what parts of this are maybe a little too pie in the sky that we should dig into, or what could use clarification. Okay, we feeling reasonably good? So let's take five. And then when we come back, what I'll do is I'll start talking a bit about some schema design best practices. We'll look a little bit at Postgres, and we'll play with some examples before we get into the code. Thank you, everyone, and I'll see you all in 5 minutes. All right. So, I've been talking at sort of a high level about what's a database, what's a relational database, a lot of the things that's important to do with our data as our programs get bigger. And we've sort of seen this diagram of how I might have a server talking to a database, and I might in fact have many instances of a database running. Um, Now, as we do this and you guys learn and do this, all of this will be on your own computer. But in the real world and in a production environment, and later we'll learn how to do this, remember that the server and the database engine or the database server are probably running on different servers over the internet. They're running somewhere on the cloud. And we might have many users talking to our server at the same time and our database as well. And that's part of the database's job too. What if, 500 people or 1,000 people per second are trying to get the Pokemon data about Pikachu? Or if we were able to modify this data, what if like 100 people at the same time are trying to modify data about Pikachu's moves? Part of what a database program does is manage those things so we don't have conflicts or overwrites or stuff like that, right? Or if you think about like an accounting system for a giant corporation, you could imagine how that becomes really important. And just to pull up, I have a couple other diagrams here as well. Um, Sort of hiding in our optional lessons, we have sort of a breakdown of this as well. And just to kind of recap, a database's job is to write data, to save it, right? We can create, update, or destroy data. To be able to read data and not just read it, but query and search it, to organize it. And relational databases do this with tables, to make sure that we never accidentally delete data that is stored, right? I can put data in a CSV file But if I make some mistake and I do rm Pokemon.csv on the command line, then that data is gone. A database will not let me accidentally delete data. Access control, right? If I'm a bank and I have a big database, I want to control who can view what information about what account. And then data integrity to make sure that if the power goes out when I'm like in the middle of removing money from my checking account, that operation either succeeds or fails, and we're not left in some terrible sort of half state. And this is just another diagram it's actually the same as, excuse me, this TL draw that I made. It's just a little more abstracted out where we have users. And in this example, we actually have two different databases running on one database engine, right? Because a database engine can hold multiple databases. So here, Postgres has a database for payroll and accounting for a company, and also like physical inventory, say for a clothing store. And we see two different kinds of users. In fact, we have three. We have a company accountant, a store manager, and a store employee. And the store manager and the company accountant are on their computers using their browsers on their desktops to talk to our app. The store employee is using either a browser on their phone, or maybe the company has an iPhone app or an Android app. Um, there's a load balancer that sends this requests to different servers. And we have here APIs for the accounting app and APIs for store inventory. And then those APIs talk to our database engine, right? And so one team that manages this accounting program, they can create a database and know that the database engine secures it so that other random users can't look at that data. And then we have an inventory database here as well. And then over here, we have us, the programmer, and we're using pSQL on the command line on our computers to talk to this database to query data or to test out new SQL for it. And I just want to pause here and see if folks have questions as well, because we've talked about a lot of these pieces, but we probably haven't seen a diagram in quite this way before. And I want to check in too. Do you guys feel like these pieces are sort of like clicking with things that we've covered previously, or that it feels like there's a lot of new information all at once? Chris, yes, sir.
Yeah, what was the load balancer again?
Yeah, we haven't really talked about load balancers yet, and it's a little outside the scope of the course. But we have seen how to make our own backend server, like a simple Flask API server, or if we go to the Pokey API, which is, I think I pulled it out, but let's go back to the Pokey API. So what if there are 500,000 people using this Pokey API all at once? Because on the internet, the whole world can, right? Um, if there's too many requests coming to a server, it'll crash it because there's more requests coming in per second than the server can handle. So a common strategy to deal with that is you run multiple API servers and you balance the traffic between them. And so a load balancer is just a fancy name for a server that balances traffic between other servers. And again, this is out of scope and more about system design, but I think it's good to start seeing these things. Arnold, yes, sir.
Good morning. If you could correct me on my understanding the way how I worded, but is this our way of breaking down bigger a big API so that it's easier for us to get requests from, and then we can go ahead and um basically get one from one data set to another. That's why it's easier. I think you're muted.
Thank you. That's a good question. Not in this case. In this case, I wanted to show two different kinds of programs, the inventory program and the accounting program, just to emphasize that a database engine like Postgres can have different databases. So the way to think about this is these are really two separate completely separate programs. The load balancing and the APIs is more about what we call scaling, which is not the removal of scales from a fish, but here we go. This is actually a great description. Scaling software is the process of increasing its capacity to handle more users, traffic, or data without sacrificing performance. This is achieved through strategies like horizontal scaling, which means adding more machines, or vertical scaling, which means upgrading existing machines. So like in this example, if I have so many people using this accounting program that this one server can't handle it, I could either choose to use like a bigger, more powerful server with more RAM and a faster processor, and that would be vertical scaling, or I could just get two of the same server and run the exact same API code on these two servers and have a load balancer distribute traffic between them. And that's called horizontal scaling. Does
Oh,
that
okay.
help?
So,
Oh, yeah,
yes,
please.
just to clarify, so they're basically just two of the same, in your case, these are just two of the same things. It's just that so that in order to offload some of it, you have to like create another one just to
Yeah,
balance it out. Okay, thank you.
yeah, exactly. It's literally like if you imagine like I'm working at the post office and I have so many people in line that I can't deal with it. Well, either I can figure out how to deal with customers faster. I can vertically scale, or I can hire another employee, and there can be two of us, and then the line gets split in half, right? Because there's two lines, and that would be horizontal scaling. Yeah, good question. And again, this is out of scope. This is more about system design. But as we start to kind of get into bigger, more complex programs, it's good to think about this. But also, it does relate to our data because it helps explain why I need a database engine like Postgres. Because one of the things that database engines are designed to do is be able to read and write data really fast. Because if I have lots of traffic or lots of users, my program needs to be able to handle that and not like accidentally overwrite data or break things. And Rick, I think you had a question as well.
Um, well, this kind of just goes back to I think you had brought it up and asked the question before, but you also got to think about like who's using the database. You've got relational databases, you've got object-oriented databases, and more recently, you know, if you're making a database for like an artificial intelligence, you have vector databases now. So, y'all also got to think about like what and who are actually using the database. I just want to add that.
Yeah, absolutely. Um, and you touched on a good point. Like Postgres is what we call a relational database. And I think the tool that I wanted here is finally working. Um, and so I might have a table of Pokemon and a table of Pokemon moves. And for simplicity, we'll just call it like move. And I think we'll just call it move ID. And we might have this table that represents moves, and the move has a name, and then just give it a description just for fun. And so my Pokemon's move ID relates to this move table. And to go back to our spreadsheet, this is sort of similar to what we saw here. Though in fact, if I was to kind of diagram that out a bit more, in fact, we would see a table here in the middle, and we can call it Pokemon move. and it would keep track of which Pokemons have which moves. And and this is just a diagramming tool. And I'll kind of break it down in just a second, but I just kind of want to put this here. Let's put that there with move ID. Let's get these things pointed to the right thing. And so this is a visual representation of what I did in this spreadsheet where I have a Pokemon with an ID and a name, moves with an ID and a name, and then this table to keep track of which Pokemon have what moves. And we'll see how to actually write the SQL to make these tables a bit later. I know we've seen a little bit of it, but this visualizes this idea of tables, which are these columns and rows that have relationships between them. And so this is, right, when we talk about a relational database, this is what we're talking about. It organizes data into columns and rows. They're called tables. There's more to it than that. And you can actually find some nice stuff in the Wikipedia on databases. The idea does actually go a bit deeper than what we're seeing here, and there is some sort of logic and math behind it. And then relational databases use this language SQL that we've seen, and that we'll see more in a bit, called the structured query language. And there's a couple different, and it's a bit of a standard, right? And you can scroll here and see all this history. And I wonder if they have an example. And they don't even have an example, but they do have all these different types, which we'll walk through in a minute. And there's a lot of different relational databases, right? There's the database that we're going to learn about called Postgres or PostgreSQL, which is open source. It actually has a lot of powerful features that we'll talk about in a minute. A very similar relational database is called MySQL, which we won't cover in this class, but everything we learn will apply to all relational databases. So once you learn one, like Postgres, the knowledge transfers really easily to MySQL, or Microsoft has one called, I think it's Microsoft SQL. And then there are other kinds of databases that do not use tables and columns. The most popular of which is what's called a NoSQL database, that organizes data differently. And MongoDB is one of the more popular ones where data is organized. It looks more like JSON, basically. So there's a lot of different kinds of databases out there. But the relational database has been around since like the 50s or the 60s. It's still popular. And this particular database engine, Postgres, actually can do a lot of different things. So it's super flexible. Tom, yes, sir.
So is and we don't have to go deep into it, but is a graph database a type of relational database, or is it like a no SQL kind of database? Because I was trying to understand it, but it's kind of all over the place.
Yeah, it's a good question. It's not a relational database. The name is a little confusing because indeed, like, there's relationships in a graph. But if you hear the term relational database, it specifically means like tables with columns and rows and SQL. Um, it looks like there's probably a bunch of different kinds of graph databases. Some might fall into the no SQL category, like the AI is saying here. Others might not. Yeah, that is a good question. let's see if they have a nice little diagram here. This is kind of going back actually to some of the stuff we saw a little bit with AI and chatbots. If you think about like how to map like parts of a sentence, like a graph database, or Rick, like you were saying, like a vector database, can be useful. And for a while, I don't know if it's still the most popular graph database, but there was this database called Neo4j that I know was popular for a while with graph databases. But I honestly don't know a ton about graph databases. And again, like Postgres and relational databases, just for folks who might be less familiar with graph or NoSQL databases, the relational database is really, I think, the right starting point and the bread and butter. And then everything that we learn here will kind of build and lead up to if you want to explore more advanced things. And Postgres actually does have a lot of those more advanced features. Um, so let's talk a little bit now about how to design good schemas or databases, right? Because here's a sort of visualization of what data might look like in my Pokemon and my moves database here. And then here is sort of a simple schema design, right, of my three tables. And let's talk about the things that we have going on. This first one is what's called normalization. And the idea here is to reduce data redundancy. And a good example of this might be if my Pokemon, you know, if I had all the information for a Pokemon move, let's put the moves here. And let's say that Pokemon moves also have maybe like a power level, right? And in fact, let's put the Pokemon moves down here. And let's say that Pokemon moves also have a description. And I'm just making stuff up. I am 100% sure that anyone who knows Pokemon is probably upset with me right now. So if I was recording all this data, and again, the thing to think about is just imagine you're writing this down on graph paper. That's always the way to start when you're thinking about relational databases. I might, want to do something like this. Right? And it might be, the awesome move has power 3 and it's an ice move. And maybe actually Charmander has the same thing. I could write down on a piece of paper information about my Pokemon like this, where I have the Pokemon's name, and we'll get rid of this column. The Pokemon's name, and like the move that the Pokemon has. There's two problems with this, right? First off, if I do it this way, how do I deal with when my Pokemon has multiple moves? I can't. I would have to start adding more columns, and it would have to look like this, right? And all this extra stuff. The other problem here is I'm duplicating information, right? This awesome move, I'm putting this data in 2 rows. And first of all, this takes up extra space. And second of all, what if I want to change the name of my move? Well, I would now have to, change it in 2 spots. And you could imagine this in, a CSV file, right? If it was move name and move power and move description, and it looked like this, awesome move, and it's power 3, and the description is ice move. I had the same thing here. So I actually have duplicate data here about my move, right? So this term normalizing, it's more complex, but the essence of it is getting rid of duplicate data and not storing the same thing in two places. And so when I start thinking about creating tables, and again, a spreadsheet is actually a really great design tool. I want to pay attention to when I start to have duplicate data, and if I can, break it out into a separate table. Right? And by putting the information about my moves in a separate table and referring to those IDs, I don't have that duplicate data. And if I want to change the name of my move, it's way easier to do that. And then I can even use, so this is called a join table, right? I want Pikachu to be able to have two moves. And I see here, let's make this red so it's easier to see. And let's make these moves. We'll make that move. We'll make it blue. And this move, we'll make it green. And I'll make Charmander yellow. And so you can see how by giving every row an ID, I can write down relationships between them, right? Pikachu has the awesome move. And Pikachu has the decent move as well. And this is getting a little more advanced, but this is actually super important. So I just want to pause here and see if folks have any questions. And if I was putting this in CSV files, I have a CSV file for my Pokemon, a CSV file for my moves, and then I might have like a Pokemon move.csv. In fact, I should have ID name. And Pokemon move, I might have an ID so I can keep track of each row separately, but then there would be the move ID and the Pokemon ID, right? And I have 1, 7, 1, and 2, 8, 2, and 3, 8, 1. And so I could write down in different CSV files these relationships, right? And I could then use this so that Pikachu, the Pokemon with ID 1, has 2 different moves. And we'll see how we can use SQL to do this in just a minute. But I want to really focus on this sort of conceptual level of thinking about how we organize our data. And we can sort of see these relationships between tables. And we can see how by normalizing, by not repeating or duplicating data, I can make my data design better, which then can help me write better code. So this is the first good practice that's really important. The next is what's called a primary key. We often call this an ID. Basically, whenever you see a column named ID, that is going to be what's called a primary key. And the idea is the key uniquely identifies a row of data. So in my Pokemon CSV, I might have a bunch of different Pokemon. What's another Pokemon? Ditto. I can't have 2 Pokemon with the same ID, right? Because now if I want to, because numbers are way easier for programs to work with and to refer to, right? Especially if I'm using references for to keep track of which Pokemon has which move, it's important that every row of data has a unique ID, and this unique ID is called a primary key. So this is really important. And so we see there's a primary key ID column here for my Pokemon table, for my Pokemon move table, and for moves as well. And Postgres and databases will enforce these rules around primary keys. Rick, yes, sir.
I was just going to ask because I can't remember if it does or not. I'm pretty sure it does, but within Postgres, you can have a I can't remember how it's just described an enumerating or sequential like
Yeah.
ID. All right.
Yeah, exactly. It's I think Postgres calls it sequential. In essence, Postgres will handle creating the ID for us. So it like increments the ID by one. So I don't manually have to deal with creating my primary keys. Yeah, totally. And that's a really good point. And that's a good example of like it seems like a small thing, but it's really important, right? And by having the computer do the work for us, we can have more reliable programs. So by having our database engine do that for us, it saves us. Um, there's also something that's called a foreign key. And basically, this is how we can refer to stuff, right? And so if I kind of look at my table visualization here, I see if I want to figure out which Pokemon has which move, I'm using Pikachu's primary key over here in this other table. So this is a foreign key in this Pokemon move table. And then in fact, this move ID is also a foreign key in this Pokemon move table. This ID column here for Pokemon move is what's called the primary key. And we can see it over here as well, where in this CSV file for Pokemon CSV, well, Pikachu has that primary key ID of 1. But over here in this table that's keeping track, or the CSV file of which Pokemon has which move, well, here's Pikachu's primary key. So when you see a primary key in another table, it's called a foreign key or a reference, right? And it's a lot sort of like a placeholder variable. Alex, yes, sir.
Um, I guess this is more design, but it's touching on foreign key. So say you have two foreign keys with the same key, or the same number. For example, you have seven Pokemon from your Pokemon table, and then you also have seven moves on your moves table. How do you differentiate the seven foreign key versus a Pokemon seven foreign key? Or the moves foreign? Yeah. The move seven versus a Pokemon seven,
Right,
all happening within the Pokemon underscore move table.
right. Good question. Let me go ahead and clear stuff. And let's just add another. Let's just make a move with ID of 1. Let's see here. There we go. And we'll call this like just basic move. And its power will be 1. We'll make it 2. And we'll just call it basic. So let's say I also want to give Pikachu a basic move. Well, let's change this to 1. Let's maybe make this, we're running out of colors here, like a really light orange. So is this sort of what you're asking, where like, it's like,
Yes.
yeah, it's like, hey, in this row of data, uh, Pokemon ID is 1 for Pikachu, and the move ID is 1 for the basic move. And the good news is this is totally fine because our relational database organizes data not just into rows, but also columns. So it knows that this value 1 is the move ID value for this particular row of data. And this value here is for the Pokemon ID for this row of data. Right, and to kind of let's touch example Pokemon to SQL. I'm not going to run this in Postgres, but just to write a little bit of man, and I don't think I need the curly brackets. Oh, my SQL brain might be failing me. I think actually we might. And then I think it would look something like this, ID. Oh man, my brain is going to totally fail me here. So I am actually totally going to
I think it's serial primary key.
yeah, yeah, yeah. In primary key or serial primary key, and it's parentheses, not curly brackets. So let's fix this. And we'll just say serial primary key, and then name varchar 20, and that's really it for our Pokemon. And then I might create a table, move, and it also will have an ID, and it also will have a name, and we'll let the moves have a longer name. And then it has a power level, which will make it an int, and a description, which will make even longer. And then create table. And this one is a little more advanced, so I'm not going to get too much into what's going on here with the foreign keys, but and I think that SQL might not be 100% correct, but it's close enough for government work and to kind of illustrate the point, which is that, right, because you have a great question here. Like, how does it keep track of what each of these numbers represents? Well, when I'm working with a relational database and using structured query language, it knows not just the values in each row, but the meaning of what each column is. And this is the benefit that we get. And in fact, let me pull up. We can in fact see this here. And you guys should in fact not use this to export SQL, but you can indeed use it to export, and it will create an SQL file based on your diagram, which we can take a look at here. Forgive me, it's jumping up and taking up a lot of space. But here we can see very similar to what I was writing. There's some alter table and some extra stuff here that we don't have to worry about, and it's doing it in a slightly different way, but we can see the same idea. What's more useful, by the way, is writing your own SQL and then importing it to generate the diagram. The diagram should really be used as a design tool. You guys should be writing out the SQL by hand to get comfortable with it. So let me in fact talk a little bit about data types and constraints. Postgres has a lot of different data types, and we'll in fact walk through them in a minute as we go through some of these bad practices. Indexes, we're not going to worry about directly, but under the hood, a database engine will sort of create its own indexes of data to improve performance, and it will create some of them by default. Consistent naming conventions is important. Try to name everything singular, not plural, or name everything plural. I think the better practice is singular. Let's actually double check. As you can see, it's a hotly debated topic. Indeed, I think singular is kind of preferred. Um, Also name everything lowercase in SQL for tables and columns. Um, and try to avoid special characters and use underscore. I think dash will actually break it. You can indeed write comments in your SQL. And there are other ways to actually document the data in the database. Some things to avoid, over designing, sort of like overcooking a meal. Um, as always, kind of the rule of thumb is do what you need and not what you don't. Um, I'll talk about null values in just a minute, but it's important to kind of specify like, hey, we need a Pokemon name, and the move needs a name because this helps make our data more organized. It's really important to be consistent with your naming. Security is indeed really important for databases, but it's a little bit out of scope for right now. Scalability is also out of scope for right now, but all of these design principles will set you up to have a scalable and reliable sort of database system. As your data gets big, you will have to worry about deduplicating data and performance. We don't have to worry about it right now. I think, as always, the good principle to follow is first make it work, then make it better. So if you need to, it's okay to make one big table, and then later on you can kind of break it down into smaller ones. So Postgres has a lot of different kinds of fields. And we're just going to kind of touch on the big ones. Uh, Primary keys, I've talked about a little bit. Serial has also come up. And let's in fact go into the Postgres docs. So the Postgres docs are exceptional, but also big. And they have a whole chapter here on their different data types. As you can see, Postgres actually has, you can create a column to store like geometric data. You can create a column to store network address types, uh, text search types. In fact, you can store JSON in your Postgres. So Postgres can kind of behave like other kinds of databases, though we generally want to avoid this, at least in the beginning. But for us, it's really the number types, and we see here there's integers, there's floats, there's a type for money, but serial will auto increase, and it's not uncommon to use serial for a primary key. There's a lot of different ways to create primary keys. Text is the next most important in Postgres. And if we scroll down, we see that there's a lot of different text types. And let's see, where is it hiding from us? There we go. No. So we'll just search this way, Postgres, varchar. They call it character types. So there's varchar and there's text. Varchar we can actually use for smaller amounts. Text we can also really use, to be honest. Postgres is actually pretty good at figuring out character sizes. So we've got varchar with a limit, or if I want like paragraphs of text, I would use the text type. We have different numeric fields as said here. So you can actually specify like how many decimal points are in a data type, which could be important for money or other things. Postgres actually has a monetary data type. And then we have date and time. So you can store just the date, you could store just the time, or you could store them together as a timestamp. Postgres even has the idea of time intervals. If we go to date time types, we can actually store a time zone in a column in our database. And we can store an interval of time, such as like 2 hours, right? Like say this calendar appointment is 2 hours long. So again, it's really the date time types that we're going to start with. And you can see here, there's a lot of configuration, both in terms of how the data is stored and how it's returned that we can play around with. And again, the documentation gets pretty dense. But the main thing is, I think, just knowing that these exist. And then finally, we have Boolean types, right? Which is true or false. Postgres will actually accept other things as true. Like if you put in 1 or yes, no, off, or 0 will count as false. But most of the time, you want to try and stick to true or false. And you can see some examples here. And then I think like the last type to mention is the null. The null type. And let's actually go up in the docs. And you can see here, like the docs are pretty incredible. They go through really everything you can imagine in depth and explaining it. And they have some examples here. And in fact, if you all have time, I know time is sort of the challenge, but they actually have a pretty great tutorial that goes all the way through a lot of Postgres fundamentals. The architecture fundamentals and stuff you can probably skip, but here from creating a database on, we're going to cover all of this, but if you wanted to sort of reinforce what we learned, I actually think the official Postgres tutorial is pretty good. But what I want to search for is null. And they have it here under constraints. So null is a value that we could put in for anything. For example, in this mock data over here, instead of a name, if this was, I could have an empty string, right? Or if there was literally nothing here, the database would store it as null. And null could be for any value or any type of column, right? A column that's a number or something else could be null. But then we can also set rules saying that, hey, this column name on my Pokemon move always to have a value, always has to have a value. It can never be null. And we'll talk more about constraints later. As you guys can see, there's a whole section here on constraints. But this is really important because by adding these like constraints and saying what can or can't be null, I can make it really easy to organize my data. Tom, yes, sir.
So like when we're getting data from our app into the database, is would like the JavaScript equivalent of null be like undefined or just not even accept a value? Like how would that equate?
Yeah, that's a great question. So data validation, like you're talking about, actually kind of has to happen in three different spots. It has to happen in our JavaScript app, like you were saying, like where we want to maybe validate form data before we even send it from our React app to our server to give the user fast feedback, right, on if their data is right or wrong. But then I'll just say user feedback. But then even once we validate it here, I need to have code on my server here to validate it again, because I could have many different kinds of clients, right? There could also be maybe someone is using, you know, like Python code, um, and their program is talking directly to our API to do stuff. So my server code, my code here for my API that I'm building, I always have to have validation logic here as well. And so here I need to check for null values, check for invalid data types and so on. And then so I can send this data back. And then finally, there's the actual constraints that I place in my data schema, because sometimes the business logic gets more complex and I might need to do like more than one thing here. So there's not one straight up and down answer to your question. It's going to depend on what we need to do. And sometimes, in fact, maybe the user might send like an empty string, but then in our code, we want to convert that to null before we send it to the database, just to use that as an example. So, and we'll actually see more of that when we get into Django. Alex, yes, sir.
Real quick, sorry, just to I guess solidify that. What were the three main validation points?
Those were just examples.
Oh, okay.
Yeah, there's all sorts of things we'll have to, basically any data that comes from the internet, our server cannot trust, right? Because what if someone malicious is trying to inject data or something like that? We'll see that Django does a lot of that for us, but in essence, you can never trust any data coming from the internet, which means when I'm writing an API, I can't trust any data that's sent to it. I have to validate everything. Yeah, good question. So we've covered like different types of fields that we can have, and we've gotten a bit of a tour of the Postgres docs along the way. As you can see, the docs are very comprehensive. On a practical level, it's really the data types part that's useful. But although verbose, I think they actually explain stuff really well, and pretty much anything you could possibly wonder about is here. Let me talk a little bit about, we've seen a bunch of different examples already with our sort of Pokemon example that we've been experimenting with. But let me talk about a couple different examples of kinds of relationships, and then we'll break and I think wrap for part one. So the relationships is really the big thing between tables, because that's so powerful. And we've seen this example here with a move and a Pokemon, and this other table, this join table as it's called, to keep track of which Pokemon have what moves. And this is an example of what we call a many-to-many relationship, because many Pokemon can have many moves, and many different moves can have any Pokemon, right? So many relationship. A Pokemon can have more than one move. A move can be used by more than one Pokemon. And this is really how you identify many-to-manys, is I just construct like this sentence. So for example, a book can a book have more than one author? This is a little bit of a trick question. Yeah, I would say a book can have more than one author, right? There's like books where one person's the illustrator, the other person's the writer. Sometimes people write books together. Now, if I'm designing sort of a library or a bookstore database, and I'm just doing it for school and I want to keep it simple, maybe I make a design decision that a book can have only one author. In the real world, we know this isn't true. A book can have more than one author, and an author can write more than one book, right? Um, a car can have only one VIN number. Can a car have more than one owner? Yeah, not at the same time, I don't think, but over time, a car could have more than one owner. Um, an owner definitely can have more than one car. Same with license plates, right? A car can have more than one license plate. Maybe not at the same time, but you get different plates over the years.
Plus, if it's stolen, you might have somebody else's license plate.
Yeah, there you go. There you go. So we've got a bunch of examples of many to many. One to one is where there can only be one of a specific thing. Like a car can have only one VIN number. So in fact, let me go ahead and let's put this over here and we'll say one-to-one relationship. And sometimes this really depends on design decisions. For instance, I used to use as an example, a person can have only one passport. And then I think someone correctly pointed out to me that's actually not true, right? If I have dual citizenship or like if I'm a diplomat, I might have more than one passport. If I'm designing a simple program, maybe for my purposes, a person can only have one passport. So a lot of the times there isn't one right answer, but it depends on how we want to design our program. Um, an employee can have only one employee ID, right? And an employee ID can have only one employee, probably. An employee only can have one email, one work email. And a company email can only have one employee. So emails and phone numbers are usually good examples of one-to-one relationships. You know, I know like phone numbers can get shared over time. And so again, it depends on the real world situation. But for learning purposes, I think those are pretty good examples. And we have, in fact, a couple examples here. And one is a pet store. And if we look at what's going on here, let's just kind of take a quick walk through this. So we often call the tables entities. When you're designing a REST API, you'll often hear them called resources. You could imagine creating a class in Python. Maybe we'd make a React component to display that information. And note how each table here, there's a primary key. So everything has an ID, right? A pet has an ID, customer has an ID. When a customer makes a transaction, there's a transaction ID. If a pet is purchased, there's an ID to track that specific pet transaction. We have here a customer with a first name, a last name. We actually need to fix that. That should say varchar. An email, this little star symbol here indicates the email has to be unique. I don't want two different customers with the same email. A pet has a name, it has a breed, it has an age. It's possible for me to have two pets with the same name, which makes sense. There's no rule saying a pet store can't have, two cats named Garfield, even though it might be confusing. And that's why this primary key ID is so important. And a pet has a price, as a customer, I can purchase something in the pet store, I can make a transaction. And when I do, it tracks my customer ID. So we call this a foreign key. We track the date of the transaction and how much the customer paid. I might want to buy a cat and a goldfish. So one transaction could have multiple transaction pets. I could have maybe a transaction pet for my goldfish and a transaction pet for my cat. And here we see another foreign key pointing to which pet I purchased. Right? So you guys can start to see how this idea of a foreign key is really powerful because now I can use this pet information in the transaction or all over the place. And I just want to pause here to see if folks have questions or stuff that we're curious about. Okay, cool. I know this is a little abstract, and then we'll take a break and then we'll start writing some SQL. Yes, I saw a question.
Yeah, question. Uh, yeah, I guess a question. So are we, and you didn't go over it, but are we going to go over like what this means?
What?
Oh, you don't see me drawn on your screen? Sorry. The
Oh, yeah,
like
that
what it means, what the different symbols mean whenever it comes to relationships.
yeah, that's a good point. So when you see that little crow's foot symbol, that means we actually have let me get my annotator out here.
It means like one to many.
Yeah, it means a one-to-many relationship. In that a transaction could have many different, we could have many different transaction pets for one transaction, right? And over here, a customer could have many different transactions, right? I'm not going to go over like all the symbols, but that is actually a good one to point out. Thank you. And so then the other example I want to walk through here, and we might look at the schools one as well, is we talked a little bit about with cars and owners. And actually, we can see that symbol here again, where a car um, could have multiple owners. Um, and we see again this sort of join table pattern where as an owner with a first name and a last name and an address. And maybe this is for a car dealership. And then the car dealership has also the cars that they've sold that has its primary key ID, the make, model, and year. And I want to keep track of who owns the cars. Well, if I own three different cars, this way I would have 3 rows in my car owner table, right? To kind of draw this illustration out a bit. And let's make a bit of a table here. And so I might own a Volkswagen Jetta. I might own a Ford Fiat, and maybe I own a Toyota Prius. Right? And this primary key on this car owner table is there to help keep track of these different rows. But here we can see one person owns 3 different cars. And then finally, we see a similar layout here for schools where I might have a student. And as a student, I could be enrolled in a bunch of different classes and have a grade for each class. Right. And so to map this one out, And let's just give our student a name just to keep it simple. Oops, excuse me. There we go. And there are different classes. And we'll have math and history, and of course, computer science. And then in each class, our student gets a grade. And so here I don't have student names. I have the student ID and the class ID and the grade. Right, so Alice is enrolled in math and she gets an A. Alice is enrolled in history and she gets a B. And Bob is enrolled in computer science and we'll give him an A. And so we have this diagram showing these three different tables of students enrolled in classes and this joint table of grades. And we see by using the primary keys for each of these table and using them as foreign keys and then as the grade, we can build a really nice data model to keep track of what student is enrolled in what course and what grade they got. And I just want to pause here to see if folks have questions. Okay, awesome. So this is really the end of part one. We've covered a lot of ground here, right? We've talked about why do databases matter? They help organize and enforce our data and give it data integrity, which I think we can really see in action here with these examples. We've seen this draw SQL site that we can use to visualize data models. We've talked a little bit about some of the real world concerns that drive the use of database engines. And then we've talked about some schema design best practices, right? And so we have some general advice here, and some examples of different kinds of relationships. And we've seen many to many and one-to-one relationships. And we've seen this sort of join table idea that's really powerful. And we've poked around a bit in the Postgres docs. When we come back, we will dive deeper and we'll get hands-on and we'll start writing some SQL and actually turn a schema design into tables, run SQL in Postgres, import CSV data, and see how to alter and modify tables. Let me go ahead and stop our recording.